Hello, welcome and good evening to the second part of the SoundBlaster programming Let's Code, and a few introducing words. Today we want to actually play something on the SoundBlaster card, and here is a little block diagram of the SoundBlaster family card, and there is a so-called bus interface chip and the DSP being just an Intel microcontroller. And the bus interface, I don't know, is probably also some standard bus transceiver or something. And it interfaces with the PC's ISA bus. And today we will use that ISA bus, which comes with a bunch of hardware interrupts that the card can trigger to alert the user program that it needs new data, for example. And that's something that we learn. And the data is actually transferred using DMA, direct memory access. And there's a chip for that in the PC as well, which talks over the ISA bus from main memory to the bus interface chip here, and which feeds it to the DSP on the SoundBlaster card. So this is all stuff that's pretty basic to the PC architecture, and I won't talk too much about that. You can read up on the ports on the PC help page that I already linked to, and I'll put another link here in the video description. But this could be a whole episode or a couple of their own, but just let's wing it for this time, because it's already gonna be a very long episode, trying to cut it down as much as possible, but it is a complex topic, so naturally it will take some time. But that's enough for now. And let's get started. We need to enhance our main function. For the playback to actually work, we need 3 different functions. An SB init function that sets up the RQ stuff and the DMA buffer. Then we want to write a play function that plays one single DMA buffer. And for that we use a good old Windows 3.1 sound. And then while it's playing, we will wait, do nothing. In the next part with the multiple DMA buffers, we will check for key presses and stuff so we can abort, but right now it's fine. It will take a few seconds at most here. And then we need a function dinit that reverses our IRQ and DMA setup. So that's fine. So first of all, we need a variable here. We mark it volatile. Volatile means that it can be changed at any point due to, for example, an interrupt, so the compiler won't do any optimizations here and treat it differently, basically. And yeah, that's what we need here. And next up would be the init function. So we'll write SB init, and in this function we will simply call an init IRQ function which sets up our IRQ handling, then a assign DMA buffer function, and we will also tell the SoundBlaster to enable its speaker. So we need to write a bunch of functions. Let's start with the write DSP function, because we will need this all the time. So let's put it right below the reset DSP function. And we will pass it a character, which is basically the command. 1 byte determines which command the SoundBlaster DSP is supposed to execute. The way we do that is, you can read that up here, reading and writing. So before data is written, we have to check the write buffer status port, that it's empty. If bit 7 is 0, the DSP buffer is empty and is ready to receive commands. So we can write this like follows. We just do a while loop, then we read from the SoundBlaster base port plus the write data register, which we will need to define. and bit 7 is 0x80. And this whole stuff is not empty if this is 0x80, so the bit is set. And we will do this until this is 0. And when this happened, we can simply write to the same port, so SB base plus SB write data, and we'll write the command. So we will have to define SB write data. Here we already have this stuff, and the reference tells us the write buffer status and the write command data are both register C. So we define SB write data as 0xC. That's good. We have the very first function that we need in our init function. Now off to the init IRQ functions, or function. That will be the next one, init IRQ. And we will have a dinit or a release IRQ also in the dinit function. First of all, we have to save the old IRQ handler or vector. Usually you call this vector IRQ vector, which is basically the currently installed handler, and we need to call it as well from our IRQ routine, because there might be some TSR or something that handles this. There we have to do two different things. It might be that we have a high IRQ introduced with the 286 and above. Those are the IRQs 2, 10 and 11. IRQ 9 is the same as 2 because it's cascaded. So if our IRQ is 2 or... oh, let's write it correctly. IRQ is 10 or IRQ is 11. We need to do something, and usually it's, I think we called it old IRQ in the last part, right? Yeah, here we already have the function to store it. So this is equal to getVect, which gets an interrupt vector for some vector, for some interrupt, sorry. And the hardware interrupt 2, for example, is akin to the software interrupt 71. So we write here if SBIRQ equals 2, then we do this. And now we can copy this whole stuff. And for 10 and 11, this is 72 and 73. This is a bit ugly, but this is due to the fact that we have the 2 in here, that we can't write it much nicer. And that's already that. Else we have a simpler case. This is for all the PC and XTs which didn't support the high IRQs. There we only have to do old IRQ equals getVect of SB IRQ plus 8. Simple as that. This will get the IRQ. And then we can set our own IRQ vector. So same goes here. Basically we can copy everything here. It's exactly the same, but this time we will have to call setVect, which takes a function pointer, and our function pointer will be called SB IRQ handler. Just copy this, So, and we of course forgot to write the software interrupt here. 0x71, 72, and 73. Alright, and other than that, for the PCs and the XDs, or every normal PC that uses usually 7 or 5 as their interrupt, we do something similar. Set vector of SB IRQ plus 8, and we set it to our handler. Alright. Then we have to do one more thing. We have to program the IRQ controller on the main board. So we have to enable the IRQ with the main board's programmable interrupt controller. How does that work? Again, we have to decide if we have a cascaded interrupt. As you can see, this is really shoehorned in the PC. So if we have one of the high IRQs, then we again need to copy all of this. A lot of copy pasting today. But we don't need to call setVect, but we need to call, we need to output to the port of the higher interrupt controller, and you can find this on the port side here with help PC Stanislavs. And if you take a look at A1, you can see the interrupt mask register for the second programmable interrupt controller. The first programmable interrupt controller can be found here on port 21. So that will be what we'll be using down there. So the question is, what do we need to write to that exact port? And we need to write whatever we read from 0xA1, and then we do a bitwise AND on 253, which basically gets the current mask and sets our appropriate bit. So next up, the two other interrupts that are possible, and those are just different values, 251 and 247. And then we also need to write the same thing to the lower programmable interrupt controller. So 0x21, as I said, is the primary interrupt controller, and we'll enable that there as well. All right. So otherwise, this is much simpler. We will take the primary interrupt controller, read from it, and then take the lower IRQ that we have, shift the one up to there because that's then the nth flag. If this is n, this is the nth bit in the flag, and negate that. And if we end this, then that bit is cleared. Oh yeah, I think I misspoke. So this basically clears the appropriate bits, same here. And we are good to go. Okay, this was pretty convoluted, I think. The interrupt getting and setting on the software side is pretty fine, but the programmable interrupt controllers, especially these cascaded ones, are a bit of a mess, I have to admit. Sticking to the lower IRQs is still fine, I think. This is pretty straightforward. You basically just set the appropriate bit to 0 in the register of the primary interrupt controller. But yeah, let's just go with this. So we have our second function here, up to the last function, assign DMA buffer. This is another slightly tricky one because DMA buffers must not cross 64 kilobyte pages, not even segments or something, but really pages, because the DMA controller that is used in the PC was actually for computers that can only address 64 kilobytes of RAM, and that's definitely not the case with the PC. So we have this weird thing here, and we need to jump through a lot of hoops to get the assignment working. Yeah, first of all, we need a temporary pointer to bytes, and we call this tempbuff. And we will also have to store the linear address of this buffer. The linear address is basically the full 20-bit segment and offsets wrote into one integer. And we need to store the two buffer pages. Right now for the single playback we don't need this, but I'll already introduce this for the auto init, because then we don't need to deal with this in the next course, because with the auto init playback we'll use double buffering. We need two different pages for the DMA controller, each being 16 kilobytes, and every 16 kilobytes we will do an interrupt and read more data. So the temp buffer now gets assigned newly, freshly allocated 32 kilobytes. These are the two pages, and this is tentatively. And we now calculate the linear address of this whole thing, and we take the segment of the pointer, and then we will shift this 4 bits to the left plus the offset of the pointer. So this gives us the 20-bit linear address. Now we will calculate the page at which the first page starts. Linear address right shifted by 16 gives us that part. And for the second page, that will be 32 kilobytes minus 1 on top of that, and then shifted 16 bits to the right. This gives us the second page. And now, so that we make that the two pages are actually on one physical page or one linear page, if the page 1 is not equal to page 2, this means the two halves of the buffer are actually on two different pages, which is bad. If that is the case, we just simply allocate 32 kilobytes again with a cast. And this is actually a hack. This works because the way the Turbo C works is it will just take the next free 32 kilobytes. And if those two are currently not matching up, we know that now we definitely get something that fits into actually page 2. And that's a weird hack, but it works. If the allocator works in a different way, allocating from wherever, this will fail actually. So you would, in theory, need to do something more clever, but it's good enough for us. And it works in this circumstance. And then we can actually free the temp buffer because it's not needed. It was on the wrong page. However, if by luck we get something that works from the start, we can just save it. And we of course also need to declare that, but we will do that in a second. First of all, we will store the page and the offset of this newly created thing. So actually we can copy that from upstairs. That was stupid. Okay, let's take this here. Let's calculate the linear address again, but this time from the final DMA buffer, be it the temp one or the newly calculated one. So that's that, and then we will store the page of this because we need to output this to the DMA controller at some point. And we also need to store the offset for the DMA controller. And this is basically just the lower 16 bits. And that's how you do that. Now we have to define the DMA buffer, page and offset variables, because we didn't, I think, yet. So let's put that here. So we have a pointer called DMA buffer. We have a 16-bit value called page and a 16-bit value called offset. And all this stuff here, these three values are for the DMA controller. Good, we have gotten pretty far. We've gotten almost everything set up. We've got the init IRQ, we have the assigned DMA buffer, we have the write DSP. So that is fine. Now we need the dinit function, which we can just copy from the init function more or less. Let's do that actually, because I think that's the fastest. Let's call this dinit IRQ, and let's do the SB dinit function as well. And we will do two things here. We will do write DSP SB disable speaker to turn off the sound output. We will release the DMA buffer because we don't need it anymore. And we will deinitialize the IRQ. And that's the funny part here. Restore the old IRQ vector. Basically the whole thing here again, set vector old IRQ. Just restoring, nothing fancy here. Just takes a lot of typing. Same here. And there's a typo. Let's see how many errors we will have when compiling this. We don't actually need this whole stuff here. Control Y, yeah. But we will need this stuff here. So to enable this stuff again, we basically do something much simpler now. We just have to... Oh, that was a bit stupid. We have to read the mask again. And then turn off our appropriate bit here. So that's 2 for interrupt number 2, 4 for interrupt number 10, and 8 for interrupt number 11. And we have to commit that as well again to the lower programmable interrupt controller. And the same here, this time without the negation, of course. And I see that we have made a mistake. Probably also further upstairs. Yep. So that's missing. And that's missing. Is it looking good? It's looking better at least. Same here. All the semicolons. All right. I think this looks pretty good. So we just need the single play, right? Oh, well, this will never work. Shall we try to compile this and fix some bugs first? Some things. Oh, a lot of warnings. Yes, we need to write the IRQ handler as well. Let's do that very quickly, because we will actually need that for playing. Where did I put my IRQ handler? Okay, syntax is as follows. Void and then something only the DOS C compilers have, the interrupt keyword. This is an interrupt handler. We'll set up the function differently. And yeah, let's go and define it. It doesn't take any arguments. And it will do something. What will it do? What we have to do actually, you can read that up in the SoundBlaster documentation. We have to read on the read buffer status register. I'm not sure if we actually defined that already. No, we didn't, but we need to. Oh, read data status we call it. Okay, that's fine. Then let's call it read data status as well. So that's the one that I want. That's the one that I want. And that will already satisfy the SoundBlaster. Then we need to tell the programmable interrupt controller, which, as we have seen, is on ports 20 and 21. So on port 20, we need to write 20, hex of course. This will satisfy the primary interrupt controller. And again, we have some special dealings with interrupts 2, 10, and 11. Here we have also to tell, we have also the obligation to tell the secondary or cascaded interrupt controller, which is listening on A0 in this case, and we also write the 20. So it knows that we have dealt with the interrupt. And actually, I will also introduce already what I need for the play function. We will set the playing status to 0, because in this case we are done. This will become more complicated. We already defined this, I think. Yeah, we have the playing volatile integer, that's good. So that's our interrupt handler, actually. I think that should do it. See if we got more errors. No, it gotten much better. Enable and disable speaker are still missing. And file names never used, but that's okay. I can live with that. Enable and disable speaker is not a big deal. So let's define some commands. SB enable speaker and disable speaker. So what are the commands here? Let's look them up. So at the back here we will find somewhere all the DSP commands here. I already saw it. D3 is turn off speaker and D1 is turn on speaker. So that's easy. Let's put a 0x D1 here and a 0x D3 here. Save it, build it. One warning and one error. And it, yeah, okay, that's true. We misspelled D init IRQ. And we misspelled it somewhere along here. Let's fix that. Okay, all that's missing is the magic play function. And well, that plus the actual playing. Let's start with the play function. That's simple. So we take a file pointer. We also need to know how big the file is. Then also, so that we don't have any noise if we do something bad, and we don't blast our speakers, we will set the DMA buffer to 0. So if we play, for example, if we can't read and play anything, we don't hear noise, but just silence. It's just convenience. You don't need to do that actually, but I think it's better. Then we will open the file with a given file name, and we'll read it in binary mode. Then we will try to figure out how big it is. So there's a very old trick to do that. We seek to the end of the file. Here we give the position. It's a 0 in long. And we say, yeah, please seek to the end. And then we can actually read out the file size by calling ftel, which gives us the position in the file. Since we seek to the end, it will be the size of the file. Then we rewind back to the beginning, which is seek set. And that's that. We know the file size, and now we can read the whole file in. I'm not gonna check if it's bigger than our DMA buffer. If it is, you're out of luck and bad things will happen. So be warned. Let's read one chunk of size file size from the file called raw file. And this is really a raw file, 8-bit unsigned 11 kilohertz. No headers or any other sample size is possible. Then we write the command set playback frequency, because we need to tell the SoundBlaster what sample rate this has. And we will tell it that it has 11 kilohertz. But wait, it doesn't work like that. Let's first declare set playback frequency. Set playback frequency, and this has now I have to think. 40, where's 40 hex? Here it is. Set digitized sound transfer time constant. And the formula for this is actually 65,536 minus 256 million divided by channels times sampling rate. You can actually factor out the 256. That leaves us with 256 minus 1 million divided by so-and-so, which is easier to handle for such small machines here. And that's what we will use. So, the formula is 256 minus 1 million, 123, divided by 11,000. All right. That should work. And when we have done this, we will set, we also need this here to be played. No, we don't need that, do we? Yes, we need. We need to tell the IRQ, the single playback function on the DMA controller how much we will need to play. And that will be file size. And we will call a function called single cycle playback. In the next episode we will do the multiple cycle playback. And we need to be saving the to be played as well. So we will have again volatile, because it might be changed in the interrupt handler. It will be long because files are long. And we'll call it to be played. So that's good. One step is missing, the mysterious single playback function, single cycle playback, sorry. Does it build, actually? Not quite. Oh, yeah. Better. And no errors anymore and warnings. Good, that's promising. The single playback function. This actually again gets a bit weird. So first of all, when we start this, we're definitely playing something. So this is for the main function that it actually waits for us. Now we need to program the DMA controller. First of all, we need to write to the mask register of the DMA controller. And what we're writing there is first we set the bit that is represented by the 4. So the 1, 2, 4, third bit, I guess. And we OR this by the SBDMA channel. So basically we're writing our DMA channel from the SoundBlaster to the mask register. Did we already define this? Probably not. So we should do this. So here we will define all the stuff for the DMA controller. The mask register, again, we can check here, should be port A, I hope. Looks about right, I would say. Actually, I will put all the registers here that we need, because otherwise I need to jump around like crazy. So what we also need is the mode register, which is B, port B on the PC. We also need the MSB LSB flip-flop, which is part of the hack to make this whole thing work on a PC. Because as I said, it's actually designed for 64 kilobyte computers. And we need to define the ports for the different DMA channels 0, 1 and 3, which are supported by the SoundBlaster cards. There are also higher channels similar to the interrupts, but we will not support those. Those are only needed usually for the SoundBlaster 16 and upwards. The older ones don't support that at all. And the Snark Barker, for example, supports only one channel, namely number 1. And so does the SoundBlaster 1 and 1.5. Alright, so we defined all the crazy DMA parts, and we can continue programming the whole device. So now we have to write outport B to the MSB LSB flip-flop, and we'll write a 0 here. That's simple. And then we will write to the mode register, and we will write here again our DMA, set the DMA bit of the SoundBlaster DMA, and then we will write the offset of the now we need to write the offset and the page of the DMA buffer, and there we will use the that's actually pretty simple. We only need to take our DMA channel and shift it by... Do I do something clever here? Or... Let's take a look. So this is basically the address register, I think. Shifted by 1. No, this should be the word count register, right? Well, anyway, we need to shift it by 1, and that should be the word count register, I guess. No, it isn't. It's the address register. That makes much more sense, because when we input 0 shifted by 1 will be 0, 1 shifted by 1 will be 2, and 3 will be 6, I guess. Well, anyway, this works. I tested it. And we need to output the lower byte of the offset first. And then we will need to output the high byte. And you do this basically just by selecting with the bitwise operation the lower 8 bits and then shifting right by 8 bits. That works. Okay, now we programmed the DMA controller, at least partially. Now we need to output the page. And let's do this like this. Let's switch. And we have the case 0. And here we simply output to what we just defined, DMA channel 0. And here we write the... Let's take a look again. So those were defined as 87, 83, and 82. This is the page portion. And we'll find that here, DMA page registers, and this is basically the hacking part of the whole DMA stuff. So here we'll write the page. That's also why we stored that earlier. And now we just need to replace this. Okay, so this is the non-hacky part. The offset is still in the 64 kilobyte range, and that's why it works fine just by this. And then we need the hacky register for the page, which is at a completely different place in the memory map or port map. Okay, now we need to tell the DMA controller how long our block actually is that we want to transfer. And this is the word count register, so we can do this terrible bit shift again. But this time we add 1, because address register plus 1 gives us the word count register. And we write the low byte again. And then we can copy this whole stuff again and write the high byte. And I hope this works. Then we need to write to the mask register again to tell the DMA controller, okay, no, I'm finished talking about the SoundBlaster DMA. Last but not least, we tell the SoundBlaster to start playing. We give it the single cycle playback command. And we also write the number of bytes that need to be played, because it also needs to know, in the very same manner that we did before, high byte and low byte, or low byte and high byte rather. And that's the end of that. Then we don't need to do anything anymore. Nothing left to play. However, I think we need to define this still. And the single cycle playback has its own command. So define SB single cycle playback. And this has command number 14, 8-bit single cycle DMA mode, digitized sound output. Let's build it. There's one error. That's fine. Mod register. It's not called mod register, it's called mode register. And what do you think? Will it run? Will it play something? It does. And once again. And again. Because it's so very nice. Okay, this is an extremely long episode, of course, but you can play stuff on the SoundBlaster now. We learned how to detect the SoundBlaster in the last part. Now we learned how to initialize the IRQ handling and allocate a DMA buffer. That's actually good for the weird DMA controller in the PC. We learned how to program the DMA controller, more or less for single cycle play. And that was also weird. And we learned how to unregister our IRQ handling, which is not that weird. And reading the file was pretty simple because it's raw. And yeah, that's about it. Next time we will learn how to play long files and do more complicated stuff. It will be almost a walk in the park because you got all the hard parts right now already done. And yeah, if you like this, please click on the like button, hit the subscribe button to get us over the 1000 subscribers. That would be so great. And share on your social media if you want to. Also leave a thumbs down if you didn't like it. Definitely leave a comment on what you liked or disliked, so we can do something better here. I hope you enjoyed it anyway, and I hope to see you soon for the last part, the auto-init playback.